Hello again, welcome back. We're going to continue. We're going to look at linear relationship still and correlation. So look at the two scatter plots that we have here. We have plot 1 and plot 2. Which one has a stronger linear association? Plot 1 or plot 2? Well, we can see plot 1, right? It looks pretty strong. So we could say that plot 1 appears to have a stronger linear association. A stronger linear association than plot 2 does. However, if you take a minute and look at this, it actually doesn't. So look at these two graphs again. Anything that you notice about them? If you notice, look at the scaling. The scaling here is going by 50s. The scaling here, they're going by 10s. So these are actually the same exact graph, they're just on different scalings. So however, it's not. However, it does not because they're the same graph. Does not because both graphs are actually the same. Okay? So what do we want to notice? We just want to notice the different scaling. So notice the different scaling in the graphs. So this one is kind of zoomed out, right? Like taken off on a plane, you see everything get really, really small and closer together. And this one is zoomed in. As you're landing, you come in and you get a wider view. So this makes it really hard. But if this was a visual only, and if I was looking at this and said, and if I gave you this, for instance, as an example, and I said, how would you describe this? Strong, moderate, weak, no linear relationship, then I would say that that looks strong, and I would say that this looks moderate. So that's a little bit deceiving. So we actually have a way to measure how strong the relationship is. And that brings us on to the next part. Okay. So we need some way to measure how strong the potential linear relationship is rather than just by a visual inspection. And that brings in our R value. And R is our correlation coefficient. So this is our correlation coefficient. And well, what does R tell us? This tells us the strength and the direction. So it tells us two things. It tells us the strength and direction of the potential linear association between the explanatory and the response variable. Okay, so this tells us the strength and direction of the potential, I'm going to say potential here, I'll address that in just a moment, of the potential linear association between the two variables that we're looking at or analyzing, between the explanatory and response variables. Okay. And we say potential because just because we have a measurement doesn't mean it's necessarily linear. We need to actually look at the data to determine if it's linear, because R is just going to tell us some kind of number. And well, I know you're interested and you want to know, how do we calculate R? This is how we calculate R, down here with this complicated formula. But don't worry, we're not going to do this by hand. What are we going to use? We are going to use some form of technology. maybe a computer program, maybe your calculator. There's different ways that we can do it. But we're not going to do this by hand, but I do want you to recognize what it entails, right? It involves x bar and y bar, so recall that these are the means, and s sub x and s sub y, that these are the standard deviations. Standard deviation of x, standard deviation of y. Moving on to the next page, we're going to talk about the correlation coefficient some more. So let's go through a few things about the correlation coefficient. So first of all, is r, or the correlation coefficient, the same number as slope? No, right? Remember, correlation coefficient is not the slope, but they do have what? Remember, they have the same sign. Does r have units like miles per hour, like slope did? No, it doesn't. Is the correlation coefficient heavily influenced by outliers? Yes, it is. And we can look at some applets that are going to show us that. Does correlation coefficient measure the strength of a linear relationship? Yes, it does. Does the correlation coefficient measure the strength of a nonlinear relationship? No, it does not. So we want to make sure we keep those in line, right? R is for linear only, not for nonlinear. Does an R value close to 1 mean that a linear model is the best fit? So we want to be careful, right? Like we've talked about R value getting close to 1. Is that the best fit? Well, does this follow, well, here's an R value. Does it follow a strong linear trend? Well, it looks like it follows kind of this path, right? But we looked at this one earlier. Was it more linear or was it more nonlinear? So was it following a line better or was it following a curve better? And we saw that, yes, it does follow the curve better. So that does not mean that the linear model is going to be the best fit. So not necessarily. And correlation, or the correlation coefficient, is always going to be between negative 1.0 and 1.0. So if you haven't already addressed this in your class, you most likely will be very, very soon. Right, let's moving down. Measurements for R. So I kind of put up this table here, and this table is not set in stone, but this is just kind of a general rule of thumb that we can go by. Anything between 0.8 and 1.0, we can say that that would be strong. By 0.6 to 0.8, we can say that's moderately strong. From 0.4 to 0.6, that would be weak. And anything from 0 to 0.4, we can look at that as no correlation. I probably wouldn't say very weak, I would say no correlation. Well, so let's make a little number line. I think that this will help, just so we can kind of see that. I think it's easier to think of this on a number line, that this would be 1.0 at the end, 0.8, 0.6, 0.4, and then over here this would be 0. And then going to the left, same numbers, we're just on the negative side. Just going by 0.2s after we get 0.4. Alright, so we have this little table here, so we could say in this region is strong, negative, here is moderate, negative, here is weak, negative. In between negative 0.4 and 0.4, there would be no linear association. So I'd probably say that instead of saying or very weak, because we'd say that that's no linear association between the two. And then from 0.4 to 0.6, and so on. And note that these measurements of R value are not set or defined to these boundaries. Other factors may have an influence on the strength of the linear relationship. However, this is the rule of thumb that we're going to use in this module or chapter. All right? And I'll see you for the next video.